The modulus of a function, written as y equals the modulus of f of x, ensures that the output is never negative. Geometrically, this follows a very simple rule. For any part of the graph that is already above or on the x-axis, nothing changes because the values are already positive or zero. However, for any part of the graph where the y values are negative, meaning the graph is below the x-axis, we reflect that portion across the x-axis to make it positive. Mathematically, we define it as a piecewise function. We keep the function as it is when it is non-negative, and we multiply it by -1 to flip it when it is negative. This is why the range of a modulus function is always a subset of 0 to infinity. Let's look at this visually. Here is a standard parabola shifted down. Notice the portion below the horizontal axis. When we apply the modulus, the negative segment flips upward, while the positive segments stay exactly where they are. Let's look at an example using a linear function. Let's apply this to a linear function. Consider f of x equals 2x minus 4. First, we sketch the original line. It crosses the x-axis at 2 and the y-axis at -4. Now, we apply the modulus to get y equals the modulus of 2x minus 4. Notice that the part of the line above the x-axis stays exactly where it is, but the part below the x-axis, where y is negative, is reflected upwards. This turns the straight line into a sharp V shape. The vertex of this V shape is always at the original x-intercept, which is 2, 0. The new y-intercept is the modulus of -4, which is +4. Now let's look at a quadratic function. Consider the parabola f of x equals x squared minus 4. The original graph is a standard parabola shifted down by 4 units. It has roots at -2 and +2, and its lowest point, the vertex, is at 0, -4. When we transform this into y equals the modulus of x squared minus 4, we focus on the section below the x-axis. The portions where x is less than -2 or greater than +2 remain unchanged because they are already above the axis. However, the bowl at the bottom is reflected upwards. The new vertex is at 0, +4. This creates a distinctive W or M shape, depending on the orientation of the original parabola. Trigonometric functions follow the same reflection principle, but the result depends heavily on the vertical shift, which we call c. If the vertical shift c is greater than or equal to the amplitude a, the entire wave is already above the x-axis. In this case, the modulus doesn't change the graph at all. However, if c is less than a, parts of the wave fall below the x-axis. These sections are reflected upwards, creating bouncing points on the x-axis. This transformation often changes the range and can even change the period of the function. Let's examine the function y equals the modulus of 3 cos 2x minus 1. The original function has an amplitude of 3 and a midline at -1. This means it oscillates between -4 and +2. When we apply the modulus, the section from -4 to 0 is reflected to +4 to 0. The maximum value of our new graph is now 4, and the minimum is 0. Look at the plot. The original peak at y equals 2 remains, but notice the sharp V shapes where the graph hits the x-axis. The original trough that was at -4 has been flipped up to become a new peak at +4. The period of the original function was 180 degrees. In this specific case, the period remains the same, but the shape is significantly altered. Let's look at an exam-style question. Sketch the graph of y equals the modulus of x squared minus 2x minus 3 for x between -2 and 4. Show the coordinates of the intercepts and the turning point. To solve this, we first consider the internal function f of x equals x squared minus 2x minus 3. We need to find its key features before reflecting it. First, we factorize the quadratic to find where it crosses the x-axis. We get intercepts at x equals 3 and x equals -1. These points stay exactly where they are on the modulus graph. The original vertex is at x equals 1. Substituting this back gives a y value of -4. Since this is negative, the modulus will reflect it to positive 4. The original y-intercept is at 0, -3, which reflects to 0, 3. At the domain limits, x equals -2 and x equals 4, the function evaluates to 5. We draw the parabola, but instead of going down to -4, we bounce at the x-axis and rise to a peak at 1, 4. Finally, we ensure the graph starts and ends at the correct coordinates for the given domain. We label the turning point at 1, 4, the intercepts at -1, 0 and 3, 0, and the y-intercept at 0, 3. Let's look at where students often lose marks in the exam. The first mistake is reflecting across the y-axis instead of the x-axis. Remember, the modulus is on the outside of the function, so it affects the y values. Only the vertical position changes, never the horizontal. Secondly, many students draw smooth, rounded curves where the graph touches the x-axis. Because the reflection is an abrupt change in direction, these must be sharp V-shapes or bouncing points. Examiners look specifically for these sharp corners. Finally, don't forget the y-intercept. If your original y-intercept is negative, say at -5, your modulus graph must have a clear intercept at +5. Here are some top tips for your revision. When sketching, draw the original function with a light dashed line first, then draw the final modulus graph in a solid, bold line. This helps you maintain the correct shape and symmetry. Always label key points. Always label your intercepts and turning points with their coordinates. Even if your sketch isn't perfectly to scale, correct labels can save your marks. In IGCSE papers, questions often specify a domain, like x is between -2 and 5. Ensure your graph starts and stops exactly at these boundaries. To summarize today's lesson, the core rule for y equals the modulus of f of x is to reflect all parts of the graph below the x-axis upwards. The transformation does not change the possible values of x, so the domain is identical to the original function. The output of a modulus function can never be negative, so the range will always be a subset of 0 to infinity. The x-intercepts of the original function become the points where the modulus graph bounces off the x-axis. Take a moment to pause the video and try these 3 practice questions. We will go through the solutions shortly. Question 1. Sketch the modulus of the linear function x minus 3 over the domain 0 to 6. Question 2. Sketch the modulus of x squared minus 6x plus 5. Make sure to clearly state the range of the resulting function. Question 3. Determine the range of the trigonometric modulus function 4 sine 3x plus 2. Take your time to work through these carefully. Let's look at the solutions. For the first question, we sketch the line x minus 3 and reflect the negative portion. For question 2, the quadratic x squared minus 6x plus 5 has roots at 1 and 5. The range of the modulus function starts from 0. Finally, for question 3, the function 4 sine 3x plus 2 ranges from -2 to 6 before the modulus. Applying the modulus reflects the values from -2 to 0, so the final range is 0 to 6.